So right now I'm going to introduce one of the most important concepts and the concept we're going to use the most as we go through this semester. And that's the normal distribution. You might also hear of it as a bell shape. So this is a histogram for the distribution of 300 natural births. The left axis shows the number of births for each day, and our x-axis shows the days before or after due date. And you can kind of see that this graph forms a normal shape. Things that occur naturally their graphs will form a normal shape. This is also called the normal distribution. It is a symmetric bell-shaped distribution with a single peak. Its peak corresponds to the mean, median, and mode of this distribution. So that means in this case, these are all equal. And its variation can be characterized by the standard deviation of the distribution. We're going to go into what this is in just a little bit. So let's take a look at both of these graphs. Are both of these graphs normal? Yes, they are. But one has a larger standard deviation, which is how we talk about how data spreads out, and the other one has a smaller standard deviation. So the majority of the data is close to the mean. The area that lies under a normal curve corresponds to the range of values on the horizontal axis is the frequency of those values. So because our total relative frequency is 1, the total area under the normal curve must equal 1. That's a really important concept. If you have one takeaway, the area under the normal curve is 1. So, a data set that satisfies the following 4 criteria is likely to have a nearly normal, so really, really close to a normal distribution. The data values are clustered around the mean. The data values are spread evenly around the mean, making the distribution symmetric, right? Because a normal distribution is symmetric. Larger deviations from the mean, so like values really, really far away from the mean. So like for instance, the mean height of people is like 5'10". It's very unlikely you're going to meet someone who's 10 foot, right? That'd be really far away from the mean. And the individual data values result from a combination of many different factors, such as genetic and environmental factors. What does that mean? These are things that are more naturally occurring. So let's talk through a few examples and see which of the following would you expect to have a normal or a nearly normal distribution. Scores on a very easy test. Would that be a normal distribution? No, right? If it's a really easy test, everybody gets A's, that's not a normal distribution. How about tree lengths in a forest? Yes, this occurs naturally. This would have a nearly normal distribution. What about foot lengths of a random sample of adult women? Feet are part of us. They're natural, right? So this would have a normal distribution. And what about luggage weights on an airplane? This is up for debate. I am an overpacker, but I don't think that this would follow a natural curve. The temperature of an oven when it has not been turned on or open for 1 day. I don't know if that'd be normal. I think that'd be just kind of flat, don't you think? If we were to graph its temperature all day, it wouldn't change. So this is a no. The empirical rule applies to data that is approximately bell-shaped. This is also called the 68, 99, 99.7 rule. Okay? What this means is that within the first standard deviation, under our curve, we'll have 68% of the data set present. Between the second standard deviation, we'll have 98% of our data present. And within 3 standard deviations, we'll have 99.7% of our data. So almost all of our data is present. The 68, 95, 99.7 rule gives us a guideline to figure out which data values occur within 1, 2, or 3 standard deviations of the mean. Remember, standard deviation is a measure of variation. So let's use the 68, 95, 90.7 rule for a couple examples. So let's assume 1,000 students take an exam and the scores are normally distributed with a mean of 75 and a standard deviation of 7. Okay, let's construct a normal distribution with this information. This is sigma. This stands for standard deviation. Okay, let's go ahead and make a normal distribution. So I'm going to draw a normal curve. Beautiful. I'm going to label my mean, which I know is 75. Remember that symbol mu means mean. And I want to go 3 standard deviations above and 3 standard deviations below my mean. So I'm going to go 75 plus 7. That gives me 82. So I've gone plus 1 standard deviation. 82 plus 7 is 89. That's plus 2 standard deviations. And 89 plus 7 is 96. That's plus 3 standard deviations. So I'm always going to go positive 3 standard deviations and negative 3 standard deviations. So if I go negative 1 standard deviation, that puts me at 68. Negative 2 standard deviations puts me at 68 minus 7, which is 61. And negative 3 standard deviations is 54. So here I have my normal distribution. Within the first, let me use a different color for clarity. Within the first standard deviation, this area under the curve is 0.68 because it contains 68% of the data. So this area right here is 0.68. If I go 2 standard deviations, I have 95% of the data. So that means the area over here is 0.95. This is really important, right? Remember, the entire area under the curve is 1. And last but not least, if I go within 3 standard deviations, I have 99.7% of data, right? So I've almost got all the data. And we're going to start to use this 68, 95, 99.7 rule to make some calculations. But the area under this curve from here all the way to here is 0.997. All right. Pulse rates of randomly selected adult males have a distribution with a mean of 70 beats per minute and a standard deviation of about 11 beats per minute. Could we consider this a normal distribution? Yes, we could. Pulse rates of randomly selected men, that's something that would occur naturally. So we can go ahead and, draw this normal curve. So I've got a mean of 70. I've got a standard deviation of 11. I want to go up. Oh, that was kind of a poor job, wasn't it? I want to go up 3 standard deviations. 1, 2, 3, and below 3 standard deviations. I'm not the best normal curve drawer, but I think you get the gist. So if I go up 1 standard deviation, that puts me at 81. 2 standard deviations puts me at 92. And 3 standard deviations in the positive direction puts me at 103. I need to go the same direction. I need to go negative 1 standard deviation. That puts me at 59. Negative 2 standard deviations puts me at 38, 48, sorry about that. And then I go 1 more standard deviation down, and that's going to put me at 37. So here we have our normal curve. Now, vending machines can be adjusted to reject coins above and below certain weights. The weights of legal U.S. quarters have a normal distribution with a mean of 5.67 grams and a standard deviation of 0.07 grams. If a vending machine is adjusted to reject quarters that weigh more than 5.8 or less than 5.53 grams, what percentage of legal quarters will be rejected by the machine? Okay, what do I have to do to solve this? Well, I know they form a normal distribution. I know that I've got 68% of data within the first standard deviation, 95% of data within the second standard deviation, and within 3 standard deviations, I've got 99.7% of data. We're going to use we're going to use the 68, 95, 99.7 rule in order to solve this problem. So I'm going to go ahead and fill in my standard deviations. If I go up 7, that gives me 5.74. Up another 7, that puts me at 5.81. Oop, look, that's a value I have. Let me stop. And then 5.88. If I go down, that puts me at 5.60, 5.53. Subtract another 7, that puts me at 5.46. So here I have my 2 data values. Well, they mark the second standard deviation. Let's switch colors. How much data is within the first 2 standard deviations? It's 95%, right? So the area point here is 9.95. Friendly reminder, the area under a normal curve is 1. So how do I find out the area over here and over here? Because that's what I want. This is where the weights of the quarters will be rejected. What I do is I take 1 minus 0.95. That gives me 0.05, so 5%. 5% of legal quarters would be rejected. Okay, so let's do another example using the 68, 95, 99.7 rule. So pulse rates of females are normally distributed with a mean of 74 and a standard deviation of 12.5. What percentage of adult females what is the percentage of adult females with, pulse rates below 49 beats per minute? So we need to go ahead and sketch a normal distribution. I need to go up 3 standard deviations and down 3 standard deviations. So if I go up 1, that puts me at 86.5. If I go up 2, that puts me at 99. If I go up 3, that puts me at 111.5. Did I math that right? Yes. Okay, now we need to go our standard deviations to the left. So I subtract 12.5, that puts me at 61.5. If I subtract another 12.5, that puts me at 49. And if I subtract another 12.5, that puts me at 36.5. Yes. Okay, so those are my standard deviations for data less than the mean, so to the left, because here's our mean, right? And I want to know what percentage of adult females have pulse rates below 49 beats per minute. Well, what 49 marks is our second standard deviation, so I want to find the area over here. I'm given one key bit of information, that the area over here is 95%, right? So 0.95. In the last problem, we wanted to find the area in both ends. We're going to call these tails. Oops. But now I just want to find the area in this one specific tail. Friendly reminder that the normal distribution is symmetric. So if I took 1 minus 0.95, that would give me 0.05. But that's the data in both tails. If I want to find the data in just one tail, I divide by 2. That gives me 0.025 and 0.025. So the area in each of these tails is 0.025. But I only care about adult females with a pulse rate below 49 beats per minute. So that's 0.025 or 2.5%. Okay, so we're going to do one more problem practicing how to use these normal distributions. So, in a study of facial behavior, people in a control group are timed as to the duration of eye contact that they make within a 5-minute period. Their times are normally distributed with a mean of 180 seconds, so 3 minutes, not bad, and a standard deviation of 55 seconds. we're going to use the 68, 95, 99.7 rule to find the indicated quantity. It says sketch a picture if you need. My recommendation is always sketch a picture. Always, always. So we've got our mean of 180. My standard deviation is 55. So I've got 55 plus 180. That puts me at 235. 235 plus 55, that puts me at 290. 290 plus 55 puts me at 345. So now I've gone up 3 standard deviations. Now I got to do the same thing to the left. Gosh, I have to write tiny. 180 minus 55, that puts me at 125. 125 minus 58, that puts me at 70. And 70 minus 55 puts me at 15. So, I think I did this right. Find the percentage of participants with times between 70 and 90 seconds. Well, I'll do this one in blue. Oh, you can't see that blue very well, can we? Okay. Changing to orange. So, 70 and 290 mark 2 standard deviations. How much data is in 2 standard deviations? 95%. Okay. Now, what if I want to find the percentage of times greater than 15 seconds? Here's 15. 15 marks the 3rd standard deviation. So I know I've got 99.7% of data over here, but I want to know everything greater than 0.15. So I want all of this and this little tail over here. So I take 1 minus 0.997. That gives me 0.003. I divide that by 2. I get 0.0015. So that's the area over here. This is 0.997. So I'm going to add those two together. And I get 0.9985 or 99.85%. Next, I want to find the percentage of times less than 128 seconds. Sorry, 125. Well, 125, we're going to have to use blue, marks the 1st standard deviation. So 68% of data is over here. That means I've also, and then for this problem, I'm just trying to find this area over here. Okay? I'm going to take 1 minus 68.68, and because I just care about the area in this tail, it's symmetrical, I'm going to divide this by 2. That gives me 0.32 divided by 2, so I get 16. Last but not least, back in the green, find the percentage of times between 70 and 180 seconds. So, it's important to note that 180 is our mean. It divides our graph in half. That means the area on this side is 0.50 and the area on this side is 0.50. And I want to know how much is between 70 and 180. 70 marks my 2nd standard deviation. That's normally 95% of the data. So if I divide that in half, because it's symmetrical, right, I get 0.475 or 47.5%. So in statistics, we often need to distinguish values that are typical or usual from those that are unusual, okay? And unusual values are values that are more than 2 standard deviations away from the mean. So everything over here and everything over here is considered unusual. We can also call those outliers. Outliers are data values that are out there. So an outlier is a data value that is much higher or much lower than all the others. As you can see from our normal distribution, over here it would be much higher, and to the left it would be much lower. So let's look at the effects on outliers. So graduating seniors on a men's basketball team receive the following first-year contract offers to play in the National Basketball Association. So here are their offers. 0, 0, 0, 0, 10,000. Is the mean a good portrayal of the contract offers students received? Well, let's go ahead and calculate the mean. That's going to be 0 plus 0 plus 0 plus 0 plus 10 million to the 6th divided by 5. You still get 2 to the 6th, so $2 million. Is that a good portrayal of what students actually received? No. $10 million is an outlier that happened to one student. They aren't splitting all the money like the mean would suggest. A better measurement could be the mode, right? The mode of this would be 0. The median would also be 0. So those would probably be better measures of center. Next, I want to talk about skewness. So depending on the way our mean, median, mode distribute across our normal curve or distribute across our data set, our graph can be skewed. So friendly reminder that a distribution of data is symmetric if the left half of a histogram, or our normal curve, is roughly a mirror image of its right half. In that symmetric data, our mean equals our median equals our mode. That's a key point of symmetric data. Here we have our normal curve, and our normal curve, mean is median is mode. If the distribution to the data is not symmetric, then it's said to be skewed. And we have two types of skewness. You can be skewed to the left or skewed to the right. So here are some skewed distributions. So symmetric, we know all about that. Now, when you're skewed, okay, we want to look at the mean. We want to keep track of the mean, okay? So skewed to the left, even though the hump's on the right, skewed to the left means that the mean and median are less than the mode. If something's skewed to the right, even though the hump's on the left, remember it's opposite time, the mean and median are greater than the mode. And symmetric, they're all equal. So remember, left skewed has its hump on the right, and right skewed has its hump on the left.